तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were discussing the applications of flip-flops. In addition to being a storage element, a flip-flop can also be used for division of the frequency by a factor of 2. Each flip-flop divides the clock frequency by a factor of 2. Also can be used as a counter by stacking flip-flops serially, connecting series of flip-flops serially. We can use it as a counter. We saw that yesterday in the last lecture. The counting was, you can start, it depends, the number of counts, the number of distinct states the counter has will depend on the number of flip-flops. So if there are n flip-flops, the number of distinct states the counter can take is 2 power n. So if you start the count with 0, go to 2 raised to n minus 1. You can also do a down counting. After all, down counting and up counting is not very different, because we know that q and q bar are always complementary in any flip-flop. So if you, in a counting, if you start the count with 0, 0, 0, let us say it's a 3-bit counter. Let us assume this 3 flip-flops outputs ABC, QA, QB and QC. So the count starts from 0, 0, 0, then 0, 0, 1, 0, 1, 0. Now if you look at the complementary outputs, this will be 1, 1, 1, this will be 1, 1, 0, so all you have to do is to use the same counter, whatever counter we had for up counting. Use the same counter, but take the flip-flop states from the Q bar. So if you looked at Q bar instead of Q of the flip-flops, you get a down counter. So I can have a 0 to 2 power n minus 1 counter using n flip-flops. and 2 power n minus 1 to 0 counter also using the same n flip-flops, depending on where I take the outputs from. If I take the output from Q, it becomes up counting Q outputs, up count. Q bar outputs, if you take, it becomes a down count. So that is a very major use of a flip-flop. Use flip-flops in a chain and for counting events. Now, sometimes I may not want to count till the end of the last state that is possible. With an n bit counter, we go from 0 to 2n minus 1 and then go back to 0. After 2n minus 1 count, the flip-flop becomes 0, 0, 0 again. So I need to go through the full cycle of modulo. I said modulus. The total number of states that the counter has is called modulus. Suppose I want to terminate the count at a count which is less than the maximum, of course. Cannot do it more than maximum. If you want to terminate the count at the count which is less than maximum and go back to 0, I should be able to do it. Example is with the 4 bits, we can have 0 to 15, but I may want to terminate with 9, 0 to 9, and start again with 0. That will be a decimal counter. A decimal counter will come from 0 to 9, back to 0. Or for that matter, I may want to start a count which a number, which a state which is more than, greater than 0. I may want to start a counter from, for some reason, 3 instead of 0, and then go to all the way up to 11 or 12 or whatever. So I may be able to start at any count and end at any count. Of course, within the range possible. With 4 bits, you can only go from 0 to 2n minus 1. 4 bits, you can only go from 0 to 2 power 4 minus 1, which is 0 to 15. The n bits, we can only, the n counter, the n flip-flops, we can only go from 0 to 2 power n minus 1. Within this range, I may want to start any count, I may want to end at any count and start all over again. How do you do that? By terminating the count and starting it again at any point, we can do that. For that, there is some extra mechanism required. In any flip-flop, whether it's a D flip-flop or a JK flip-flop, we're talking about, let us take a JK flip-flop because that's what we have been using for these counters. Clock, it's 0, with the 0 it becomes a negative edge triggered with an arrow and a bubble, right? That's what I said. Q and a Q bar. This is what we have been depicting a flip-flop as until now. Now I want to introduce 2 more inputs to this flip-flop. Of course, there are 2 more inputs already, which is the power supply and ground. No circuit will work without power supply and ground because these are active devices like transistors, either bipolar transistors or MOS transistors inside this. Since we have not gone into the circuit details, at most we have gone into the gate level details, not beyond that. Gates have transistors, components. Gates have active components like transistors and MOS devices. Let us not get into that, but we need to power up those devices. We need VCC and ground or VDD and ground depending on the nomenclature. Leaving those 2 inputs, power supply and ground, apart, there are 2 more inputs defined for many of these flip-flops. These are called preset and clear. This input is called PST, stands for preset. CLR stands for clear. So clear input, preset input. What does a preset input do? As you see, there is a bubble here. That means it's an inverted input. An input which activates the circuit when it is low is called an active low input. Such inputs we draw with a bubble. An input which will be effective when you make it 0, that's called active low. Input which will be active or which will activate the required thing, when you put a 1 on it, it's called active high input. We don't, when you draw a input with a bubble, it says is active low input. So the preset input, when it becomes 0, what happens is it makes Q1 irrespective of the values of j and k and irrespective of the clock is positive, clock is 0 or 1. That means the preset input, what is called in the terminology in digital, in electronic circuit parlance, overrides all other inputs. PST is equal to 0 makes Q is equal to 1. Irrespective of the value of j, k and clock at that instant of time. And as long as preset is 0, output continues to be 1. In between, a clock may come and go, we may change j and k, regardless of all that. Okay? So such an input is called an overriding input. Likewise, a clear input will make, as the name suggests, it clears the output, means Q will become 0. These happen irrespective of j, k and clock. So these two inputs are called, as I said, overriding inputs. So you need extra logic. Not do that, you can get into this a little bit extra logics, where you have to make sure that this has an overriding property of making the output 1 or 0, as the case may be. So that means I can now write a table which is called a preset clear table, and preset clear Q. Preset is 0, clear is 1, output is 1. Preset is 1, output is 0, output is clear is 0, output is 0. When preset is 0, preset is 1 and clear 1, then and only then the flip-flop functions normally, taking j and k into input, j and k as the inputs and the clock cycle. At the clock cycle it goes past high or low, all that will be determined. Only when preset and clear are both made 1, they will have no influence on the normal functioning of the flip-flop. So the flip-flop acts normally. As defined by the inputs and the clock. When you say normal, the behavior depends on the values of the input j and k and the clock. And if both are 0, which is predominant or there, because each of them is a pre-overriding input. When both are 0, which is overriding, we don't know that. So one of those states which is not permitted. Don't try to do both clear and preset 0. That means there's an uncertainty there. And I always tell you the uncertainty should be avoided at all costs in any design. So not use. Make sure you will not make preset and clear 0 at the same time. Make sure that preset and clear are not made 0 at the same time. Now this property is going to help me to start or count anywhere I like, end my count anywhere I like. Suppose I go from 0 to 2n minus 1, 2 power n minus 1, and at some intermediate point I want to terminate and make it 0, 0, 0. I can do that by detecting that point and clearing all the flip-flops at that point. Similarly, I want to start at a count other than 0. I detect the point at which I want it to happen and use my preset inputs to get the flip-flops with different values. So use preset and clear inputs to get the flip-flops to different values other than the normal sequence. That is where you get an arbitrary count counter arbitrary. It can start arbitrarily and end arbitrarily. Of course, defined by you. Arbitrarily, I don't say it's random. Arbitrary. That means you can decide what you want. So let us take a simple example of a 3-bit counter. Whether it is up or down doesn't matter, because as I said, all you have to do is to take Q or Q bar for up and down respectively. So a 3-bit counter will be 3 flip-flops all of them are JK. Okay. One. Clocks. This Q and this Q bar. So I will call this A, B, C 3 counts. A is the most significant bit and C is the least significant bit. So this should be A, QA, this is QB, this is QCR. We want to call this A, this is A, B, C. So I have A, B, C. Normally I go 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, or if I take the complements, it will be 1, 1, 1, 1, 1, 0, so forth to 0, 0, 0. I have just drawn up counter. You can also draw the down counter by taking Q bars instead of Qs. That's what I said just now. Now let us say I want after 5, 0. That means I want count from 0, 1, 2, 3, 4, 5 and back to 0. I don't want the count 6 and 7 to go through. For some reason, I want only 6 states to be counted. So all I do is to detect this when 5 is reached, clear all the flip-flops again by using the clear inputs. So all these flip-flops are clear input and preset inputs. So I detect the count that I want to count, and till that count reaches, I will have to clear them. But I cannot clear it as soon as 5 is reached, because if I clear it as soon as 5 is reached, assuming there is no delay in the clearing operation, I just reached 5 and it is cleared. That means I will go 0, 1, 2, 3, 4 completely done, 4 is completely done, 5 has just started, but I want each count to last for 1 clock period, isn't it? I want each count to last for 1 clock period. So after 0, 1, 2, 3, 4, as soon as 5 is reached, assuming there is no delay in the process of reset clearing, as soon as 5 is reached it becomes 0. That means I will not have 1 full clock period for 5. So really I should start looking at 6. When 6 reaches, if I want to terminate at 5, I should wait for 6. As soon as 6 reaches, assuming there is no delay involved in the resetting process, assuming there is no delay involved in the clearing process, as soon as count 6 is reached, I clear all the flip-flops, so it starts from 0. So it will go from 0, 1, 2, 3, 4, 5. Even 5 will last for one entire period of clock. And moment it becomes 6, immediately I will clear it. So there will be a small glitch. I refer to glitch in one of my previous lectures. A glitch is a very narrow variation in the output, very small duration, short duration output variation from either 0 to 1 to back to 0 or 1, 0 back to 1. A pulse of going from 0 to 1 back to 1, 0 to 1 back to 0, or 1 to 0 back to 1. It could be that there's a small glitch because of the small time delay involved in the clearing circuitry. There's a circuitry involved, right? If you neglect that, the other alternative is for me to have the clock count 5 only for a very, very narrow period, which is not correct. I don't want that. I want full clock period for 5 also. So actually you clear, if you want to terminate at count 5, you clear it as soon as 6 reaches. So how do you do that? I detect state 6 and use the state 6 to clear the. So state 6 is given by 110. This is count 6. Count 6 is 110. When 110 is reached, I should clear immediately all the 3 flip-flops. That means I should take this into an AND gate. One 10 becomes 111. This is 0. When 110 is reached, this is 0. So 3 input NAND gate. It will give a 0 output when this becomes 110 or this becomes 111, and this is what I will connect to the clear inputs of the 3 flip-flops. So the clear inputs of this flip-flop and where are these A, B, C coming from? B, C. In order to not clutter the drawing, I put it here. These A, B, C are not different signals. These are the outputs of the flip-flops. A is the output of flip-flop, this MSB flip-flop, this LSB flip-flop, and this in-between flip-flop. So as soon as the flip-flops A, B, C take the value 110, this becomes 0. So I would have a count 0, 1, 2, 3, 4, 5, and momentary short duration count 6, which can be ignored as a glitch, and then start all over again 0. So I can use this to do anything now. I can start at any end. If you want to start not at 0, I connect it appropriately to preset and clear. Suppose I want to start with 3. So the second example. Suppose I want to start at count 2 and yet end at count 6. I want counts 2, 3, 4, 5, 6 and back to 2. This is the cycle I want. I don't want to count 0 and 1, I don't want to count 7. So again I do the same thing. I look at 6 I have to complete. So I cannot detect when 6 is, when the flip-flop reaches the count of 6. I have to wait for count 7 to come up, because 6 has to be completely allowed. So when count 7 comes up, which is 111, I detect that and not clear all the flip-flops. In this case I will preset this flip-flop and clear these 2 flip-flops. Correct? So I will get the count 111. This is ABC. This pulse will be used to clear A and C. Clear A and C and preset B. Preset will become 1. So 2 will start. After that 2, 3, 4, 5, 6. Back to 2. So by using this preset and clear inputs, I can start the count at any point and can terminate the count at any other point. Any count you can start. And if you want a down count, all you have to do is to look at Q bars instead of Qs. So I have an up count, a down count, an arbitrary starting point, arbitrary ending point. And number of flip-flops decide the number of counts. Total maximum number of counts possible is 2 power n when n is the number of flip-flops. Since 0 has to be counted as one state or one first count, the maximum count you can reach is 2 power n minus 1. So this is how you count. As I already said, counters are used to count people, to count events, count things. Clock division is used. All the flip-flops are very, very useful circuits. Many, many applications you will find uses of flip-flops. We will see some more of them, many more of them. Do you have any questions? So in order to complete the drawing, if you want to draw A, B, C, this is my C, B, A, Q. I will not show the rest of the drawing of J, K, etc. You know what it is. All J's are 1, K's are 1. Now, A, B, C, when it reaches 0, 1, 1, 1, this becomes 0, you count this to the clear of clear. And what is it? This is my input clock. This is a counter which counts from 2 to 6. Yes?
So here only in the second cycle it starts counting from 2. So in the first cycle it's counting from 0 to 6.
Yeah. It's always, any circuit, there is a transient state. There is not even a guarantee that it is going to start at 0. When you switch on the flip-flops for the first time, the clock, arbitrarily, the clock is applied, arbitrarily the counter can reach, first counter may be 1, second counter may be 0, third counter may be 1, or 1, 1, 0, it can be anything. Very first cycle of count, you are not guaranteed of any starting value. It could all be 0, it could all be 1, it could be anything else. But moment the second time that count reaches, so there is a transient stage. The circuit has to settle down. Once the circuit settles down, it does what we want. You never take into account the initial state after a switch on the power. First time when you switch on the power, there is no guarantee the flip-flop is going to start at 0, 0, 0. Is there? No. Flip-flop may be, B may be 1, A and C may be 0. Then it's what we want, 2. On the other hand, 1 and 2 may be 0. 1 and 2 may be 0, the other one may be 1, this is 0, 0, 1 or 1, 0, 0. So you have to go for 1, 0, 0, 1, 0, 1, 1, 1, 0. When 1, 1, 0 comes, it goes to 2. So the cycle. So the initial portion, it's a transient. In linear circuits, it's called transients. You don't talk about transient. Only with the steady state, a stable state, you analyze the circuit. In this case, you can call it latency. In digital terminology, digital parlance, they call latency. Latency is the time you have to wait for the circuit to start working after you give the inputs. Latency. This is a very common word. Latency is the time at which the circuit starts delivering the output after they switch on the power or after giving the inputs. So there is an inbuilt latency in any circuit. So good question. Any other questions do you have? So now we have seen counters, and we can design any counter. We can count up to 128 if you want to, 0 to 127, or anything else also. For example, a clock. Think of clock. Somebody gave an example of a clock being a divide by 2, example of a division of frequency. We have a very high crystal frequency. These clocks run on crystal clock, the watches, the watch chips. Call it clock chips, or clock is not confused with this clock. So let us call it watch. A watch chip, an IC, integrated circuit, which used in the watches. It has its clock. This clock is derived from a very high frequency source, very high frequency stable source. It's called a crystal oscillator. That's a crystal. It is generally easy to build crystals of very high frequencies. It's very difficult to get a crystal of 100 hertz or 10 kilohertz and things like that. Usually megahertz and several megahertz is the crystal frequency that is given to you, available with stable frequency. What do you mean by stable? The frequency will not drift. Because we don't want the clock period. Some of these cheap watches, wristwatches you buy in some of these shops, bazaar. Now what happens is, you think it's a good watch, you buy for 25 rupees. Moment you start wearing it, next day morning you look at the watch, it's already 9 o'clock in the morning when it's 5 or 6. Or the other way, it is going slow at 2 o'clock. The reason is because the frequency is not stable. It counts down, 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 but then if the original crystal is not a stable frequency, it will either lose time or gain time, which you don't want. So this division by a factor of whatever required to make a clock. So I will give us an assignment, an exercise. Assume a crystal clock of, let us say, what? Very high frequency, megahertz. I wanted to find out how many stages of counting are required so that I can have a count of seconds, minutes and hours, not beyond that. I want an hour display, a minute display and a second display in my clock. So the watch has to, the crystal clock, the crystal frequency clock has to be brought down to the hours, brought down to the minutes, I mean the other way, very, very high. You do several divisions to make it one cycle per second to count seconds, then divide by 60, you get 1 cycle per minute, divide by 24, divide by what? 60 minutes make 1. Okay, divide by 60 to make it 1 hour. So I am not giving you a clock exact frequency because I want a whole number finally. So you can do it's a multiple of the clock because 60 times 60, 3,600. 3,600 seconds make an hour, right? 60 minutes make an hour, 60 seconds make a minute. So 3,600 seconds make an hour. So let us say multiply it by, okay, make it 3.6 megahertz. I am having a 3.6 megahertz clock given to you. Design a series of counters so that I can get my frequency divided at the right time, the right numbers to have a count of seconds, count of minutes, count of hours. Okay? It's an exercise. Now one disadvantage of this counter, these counters, we use the clock, we feed a clock to the very first stage of the flip-flop, very first flip-flop stage. Output of the flip-flop is used as the clock for the second stage. Output of this flip-flop is taken as the clock to the third stage. The clock is passed from flip-flop to flip-flop. There is an inherent delay, as I said. We also talked about a small glitch. Moment I reset it, it's not going to get reset. There is going to be a short time duration, depending on this. Once a 110 whatever is reached here, there is a small delay here. It takes its own time to become 111. Its own time to become 0. That 0 applied here, here, here. It has to activate the circuitry for clear to become 0, 0, 0. There is a small amount of delay involved. That is a short pulse. I said it's a glitch. You can ignore it. Now each of these flip-flops has also the propagation delay. I told you the flip-flops have this initial stage, clocking stage, and the next stage, the latching stage. So there is a propagation delay involved in each of the flip-flops. So I give this clock, it takes a while, a small amount of time though, propagation delay time. before the output changes. That is fed into this, and this is going to take its own time before this is going to change, and this is going to be applied here. This is going to take its own time, and this is going to change. So when a count, let us say a count is, let us go through this. Supposing I have this count, and I am applying the clock here, the next count is this. This 1 has to become 0, first flip-flop, C flip-flop has to become from 1 to 0, B flip-flop has to become from 1 to 0, A flip-flop has to become from 0 to 1. I am feeding the clock to the C flip-flop, as you can see there, C flip-flop. So it is going to take its own time for this 0 to, this to become 0. After that delay only, this flip-flop will go from 1 to 0. After that delay only, this 0 will go to 1, this 1. So from 0, 1, 1 to 1, 0, 0 to settle down, it is going to take a finite amount of time. Is that right? Equal to, approximately equal to 3 into propagation delay of flip-flop. We call T sub P, T subscript P as the propagation delay of a flip-flop. I want 3 propagation delays approximately. Of course, there are other things like reset, clear, all those things, preset, clear, and all those. I am not taking into that. See, once you have a number, you can always compute. But you should know there is a concept here. You should know there is a number you have to look for. Once the number is given to you, I can make it approximate now 2 nanoseconds. But later on you find from data sheet it's not 2 nanoseconds, it's 3 nanoseconds, it's all right. You have to do a computation. But you should know there is something like that we have to take into account. So there is a delay in each flip-flop stage which affects the change. And more number of flip-flops there is, the delay in counting becomes longer and longer, right? So if you have 8 flip-flops and 8 stages, with 8 flip-flops what count can I reach? Flip-flop propagation delay. Let us assume Tp to be the propagation delay of a single flip-flop. So we have 8 flip-flops, 2 power n, 2 power 8 for your 8 as an example. For 8 flip-flops, delay is 8 Tp. So what is the count I can reach? From 0 to 2 power n minus 1, n is 8. 2 power 8 is what? 256. So for a count from 0 to 255, each count takes 8 Tp to materialize. If I am 0, after 8 Tp, 0, 1 comes, after 8 Tp, 2 comes, and so forth. Reliably, of course, something can happen faster than that. There may be no, for example, here to here, there is no change in this flip-flop, so it is going to immediately come. There is no change, there is no question of propagation delay. It is not that each count is going to change only then. So I should allow for a maximum propagation delay of 8 times Tp in order for a count to be reliable. Now if we are talking of these clocks, the watches, I told you just now, from 3.6 megahertz you have to count down to a second, right? 1 second is 1 hertz per 1 cycle per second is 1 second, and megahertz is 10 power 6 times and 3.6 times. So 3.6 million to 1. You will have to find out the number of flip-flop stages required. When that is the number of flip-flop stages required, each count is going to take that much longer to materialize. Correct? Now if I run it at a speed which is faster than that speed, So my clock is slower than 8 TP. My clock period, if clock period, what do you mean by clock period? I defined it the other day. The period is starting from one point in the clock exactly till the next same point in the next period, next clock cycle. If you take the positive edge of the clock until the next positive edge comes, what is the time duration? That is called the period. If you take the negative edge from one negative edge to the next negative edge, is the clock period. So this clock period is much larger than, then you are not worried. It's a small amount of time. Anyway, it's going to have one clock period to settle down. The count is not going to change for one clock period. Every clock period the count is going to remain. From 0 to 1 to 2 to 3 to 4 to 5. Each of these counts is going to remain for one clock period. What if it takes 8 TP to settle down? 8 TP is an insignificant part of my whole clock period. But supposing I have a number of stages more, if n becomes large, clock period may approximate the value of the propagation delays of the n flip-flops. Each flip-flop has a propagation delay of Tp, and n flip-flop stages will have n time Tp, and n is very large. So I cannot run this counter at a speed faster than this NTP. So maximum clock period has to be less than NTP. If I run my counter faster than this, before the count settles down, the next count has to come. All counts are arbitrary then. In that case, it's not reliability is not there. This is what I've been stressing all the time. You cannot reliably say the count has reached from 0 to 1, 1 to 2, 2 to 3, 3 to 4. It keeps changing constantly because the clock keeps coming, and sometimes it may be right depending on the number of transitions, sometimes it may be wrong. We don't know which is right, which is wrong. So I have to either use very small number of flip-flops, that is a limitation, or use extremely low clocks, low frequency clocks, which is not always possible. As I said, the crystal oscillator was stable oscillators. There has to be crystal, and these are only available in megahertz range. So either that you cannot reduce the clock frequency for the reason of stability, not always, sometimes it is possible, not always, or you want a particular speed of counting. For my application I need to count it this fast. Events keep coming. If number of people I am going to count, if people keep coming constantly, or some small events, some atomic event or something, you are counting, keep counting at the rate at which it has to come into the count. You cannot say I can only count at this rate, so please slow down. I cannot say that. Wherever it is possible to slow down your event or slow down your increase the clock frequency, there is no problem. Or have the less number of flip-flops, there is no problem. But there may be situations where the events happen fast, because of that I need to use a high frequency clock, and the number of clock stages also, number of flip-flops stages is also large because the count has to be reached a very large value, then this counter fails. So this counter, which is called a ripple counter, suffers from the fact that the clock has to ripple through the flip-flops. Each flip-flop clock is the output of the previous clock. I give the clock to the original clock, to the first flip-flop. The output of that flip-flop is given as the clock to the second flip-flop. Output of the second flip-flop given as clock to the third flip-flop. The clock doesn't directly get into the flip-flops. The clock that is given to you as a circuit in the crystal oscillator, whatever I said, that clock doesn't directly go into different flip-flops. It only goes to the first flip-flop, and it has to ripple through like a wave in the ocean. It has to go into this, into this, into this, into this, into this. And each stage it accumulates a delay because of the propagation delay of the flip-flop. So the clock accumulates delay, and if the number of stages is larger than the events, number of stages is very large, the propagation delay is longer than the frequency of the events. The the distance between two events, the time difference between two events, then you lose track of the count. So ripple counter, the very name suggests it's a ripple. The why it is called ripple counter is because the clock is not directly applied to all the flip-flops. The clock is applied to the first flip-flop, which ripples through the different flip-flops to different stages. The ripple counter fails if the number of stages is very large, such that the total propagation delay is of the order of, I won't say mathematically it should be larger, but even in a practical electronic circuit, when it approaches the order of this clock frequency, clock period, the total propagation delay approaches the order of the propagation delay, it will fail to be a reliable circuit, because it can never predict exact values. So I have to think of, I like flip-flops being used as counters, gives you a lot of things. As I said, it can do a division by 2, you can count up, count down, start any value, end any value, and counting is one of the important things we do in many application systems, but ripple counter has to be replaced with some other counter. So the improvement of this ripple counter is called a synchronous counter. We will talk about it in the next lecture. A synchronous counter in principle is which will take care of this problem. So ripple counter suffers from the problem of too many stages and propagation delay affecting the total number of count I can use it for. On the other hand, a synchronous counter is what which is more practically used. In a synchronous counter, all flip-flops receive the clock at the same time. There is no question of clock ripple through. The clock that is given, this crystal clock or whatever clock you decide for the circuit, the stable clock, is given to all the flip-flops. So they are all clocked all the time, but the change will depend on the previous count, because if all the flip-flops are given the clock and all the flip-flops change up and down, then I can only count from 1 1 1 1 1 to 0 0 0 0. If there are only all of the toggle flip-flops, all are toggle flip-flops, so one state is all 1 1 1 1 1, other state is all 0 0 0 0. That I don't want. I will be able to get all intermediate counts also. So we will see how to use a flip-flop whose flip-flops whose clocks are all tied together to the same clock. That is, the given clock is applied to all the flip-flops, not to the first flip-flop alone, but at the same time how to get a different count. These are called synchronous counters. We will see it in the next lecture. Before that, you can do a lot of work on these ripple counters. What we have given you is a flavor. I would like you to design exercise on ripple counters. Design counter for 10, down counter for 10. So these are called decimal counters. Goes from 0 to 9 or 9 to 0. And any other value you can also do, as I said, by using these gates. We also gave you the clock watch example. These are the assignments on these ripple counters. But actually in watch we will not use a ripple counter. Finally we will say that because watch has so many stages, you will see that it may not be worthwhile to use a ripple counter. We may have to use a synchronous counter. So we will talk about synchronous counter in the next lecture.